So we're in section 10.3. Area of regular polygons. So first off, let's remember, what do we mean when we say a polygon is a regular polygon? What does that tell us about the polygon? All the sides are the same. And since the sides are the same, what else does that tell us are the same? Angles. All sides and angles are congruent to each other. So I'm going to just say congruent. So all the sides are the same, all the angles are the same. And we'll draw a picture of a regular polygon here. And I'm just going to use a pentagon for our examples, but remember, a polygon can have any number of sides. So I'm just using a pentagon for an example. This is the center. And if I connect, we're going to be doing a lot of this with regular polygons, drawing triangles here. If there's kind of a go-to technique when it comes to polygons, it's draw the triangle. All right, so I'm going to draw a triangle here. This angle, if we start at the vertex here and go to the center here and go to a vertex, is the central angle. Do you remember how to find the central angle, the measure of a central angle of a polygon? Got a nice easy formula. Remember? 360 degrees divided by the number of sides. So we can always find the central angle of a regular polygon. Just divide 360 by the number of sides. All right, I'm going to draw another regular polygon here. We have some other parts that we need to know about. So there's our center. And I'm going to draw another triangle in here. Like so. And we're making this a right angle. This side from the center to a vertex is called the radius of the polygon. From the center to the middle to a side, perpendicular to a side, is called the apothem. And this, I'm going to do this, I don't want to do it. This is half a side. So when I go perpendicular to the side, this red segment cuts this entire side in half. And this angle is half a central angle. So this little triangle that I drew in red, that's going to be very important when we're dealing with polygons. Drawing this triangle, figuring out these angles, figuring out the lengths of this, the radius, the apothem, all of that. That's going to be our big tool when we're working with regular polygons. All right, questions there so far? So let's do an example finding some angles in a regular polygon. So I'm going to use a pentagon again, just because that's what we're using now. That doesn't mean that a pentagon is the only kind of regular polygon. So this is a regular pentagon. And I'm going to draw in some angles that we're supposed to find. And we want to find, for this problem, we want to find the measure of angle 1, measure of angle 2, and the measure of angle 3. Well, what's going to be the easiest to find here? What is angle 1? What kind of angle? Angle 1 is a central angle. And we just talked about a formula for finding the central angle. So how are we going to find the measure of angle 1? Measure of angle 1 equals what? 360 over 5. And do we remember what that was for a pentagon? 72 degrees. All right, which is the next easiest to find? Angle 2. How is angle 2 related to angle 1? Half a central angle. So that's going to be 72 divided by 2, which is 36 degrees. And now we can find angle 3, right? What do all the angles in our triangle have to add up to? 180. So the measure of angle 3 is 180 minus 90 minus 36. And that comes out to be 54 degrees. We can always do this process with a regular polygon, no matter how many sides it has. We can find all of these angles. And being able to find those angles is going to be important for what we do. All right, now we have some background. Questions on that example? Now we have some background. We can talk about our formula. Area. Area of a regular polygon. Our formula is the area equals 1/2 the apothem times the perimeter units squared, where A equals the apothem and P equals the perimeter. So let's draw a picture to go with this, and we'll do a hexagon this time, so we're not using the same one every time. So there's a hexagon, there's our center. The segment that goes from the center perpendicular to a side, that's the apothem. And how do we find the perimeter of any shape? Add up all the sides around the outside. So let's talk for a second. So easy formula, not a difficult formula. The challenge is usually finding pieces that we need. Well, let's talk about where it comes from. I'm going to draw a little triangle here in my hexagon. What's the area of a triangle? How do we find, what's the formula? 1/2 base times height. Well, isn't the base of this triangle that I drew in red the side length of the polygon? Isn't the height the apothem? So the area of one of these triangles, this triangle that I drew in red here, is 1/2 the side of the polygon times the apothem. Well, there's 1/2 the apothem. If I add up one of these triangles for each of the sides, I'm going to have a side length, a side length, a side length. I'm going to have 6 side lengths. Well, if I have all 6 side lengths, what does that give me for my perimeter? That's where the perimeter comes from. This formula is finding the area of one of these triangles for each side of the polygon. So that's why it looks like the area the triangle formula. But we have the perimeter because we have all the side lengths added together because we're adding up however many triangles we have for the number of sides we have. That's where that formula comes from. It's not some secret magic, just the area of a triangle, and we're adding a bunch of them together. All right, questions then? So what I want to do is do a couple of examples where we have the information is pretty easy to get, and then I want to talk about some where it gets there's a little more work to do to find our pieces. So let's start with an easy one. So all of these, we're saying all of these are regular polygons. So I'm not going to keep writing regular polygon. This is a regular polygon. That's 12 centimeters. And this segment is 8 centimeters. And we want to find the area. Do we have all the information we need? What piece is this? That's the apothem. So A equals 8. And the perimeter, how do we find the perimeter? 12 times 5. Each side is 12, and we have 5 of them. And 12 times 5 is 60. So the area equals 1/2 8 times 60. And 1/2 is the same as dividing by 2, so I can multiply this, divide by 2. I could divide one of these by 2 and then multiply everything together. When I do all the work, I get 240 square centimeters. All right, questions there? So this is about the easiest example. What if we had one that looked like this? And again, I'm using pentagons, not because pentagons are the only kind of polygon, but that's just what I happen to pick to use. All right, and we're doing the same thing. This is a regular polygon, and we want to find the area. Do we have everything we need here? Is this piece the apothem? What is this? What part of our polygon? That's the radius. So what do? We're stuck. We can't do the problem. Well, what piece do we need? We need the apothem. Let's draw it in. Use our go-to technique of drawing our little triangle. There's the apothem. Well, now that we've drawn that in, can we figure anything else out? How long is that? Half 14, that's 7. Well, now I have a 90-degree right triangle, and I know 2 of the sides. What can I use? Pythagorean theorem always works for a right triangle when we know 2 of the sides. So I can say a squared plus 7 squared equals 11.88 squared. So a squared plus 49 equals 11.88 squared is 141.13 about. So I subtract 49 from both sides. I get a squared equals 92.13. Take the square root of both sides to undo that square. And I get that the apothem equals 9.6. So now we have the apothem. we can find our area. So the perimeter equals, how do we find the perimeter? 14 times 5, which is 70. 5 times 10 is 50. 4 times 5 is 20. 15, 20, 70. So the area would be 1/2 the apothem, 9.6 times 70. And we could calculate that out. So I'm not going to calculate it there. That's how we would calculate it. So sometimes we have to use a Pythagorean theorem to figure out our area, to find our missing piece. All right, questions on that example? All right. Well, some of our polygons, because of the way the angles work, we end up with special triangles in our polygons. So we're going to talk about three different cases where we end up with special triangles in our polygons. First one is a square. And I'm going to draw a couple of pictures of squares here. Square is a polygon. And we can talk about the center of a square. We can talk about the apothem and the radius of a square, just like any other polygon. And this is half a side. And when I take my diagonal through the center of the square, what is this angle? It cuts that angle in half, so that's a 45-degree angle. And that's a 45-degree angle. So inside a square, we have a 45, 45, 90 triangle. And we can use our special right triangle rules to find missing pieces for squares. And I can also, a lot of times it's easier just to divide the square in half. That's how we came up with our 45, 45, 90 rules. That's also a 45, 45, 90 triangle. So inside a square we have 45, 45, 90 triangles. We can also talk about equilateral triangles. So here's my triangle, equilateral triangle. I'm going to draw a couple of those also. What's special about an equilateral triangle? What do we mean when we're talking about an equilateral triangle? All the sides are equal, and all the angles inside the equilateral triangle they're the same, so they have to be how many degrees? 60. We have 60-degree angles. That should give us a hint of what kind of special triangle we end up with in an equilateral triangle. There's our center. There's our apothem. There's our radius. So there's our center, there's our apothem, there's our radius. And for our equilateral triangle, that's a 60-degree angle, that's a 30-degree angle, and that's half a side. So we end up with a 30, 60, 90 triangle inside an equilateral triangle. And a lot of times with an equilateral triangle, I like just to divide them in half. That's how we came up with our 30, 60, 90 rule. And that's a 60-degree angle. And that's a 30-degree angle. And this is the height of the triangle. So in equilateral triangles, we end up with 30, 60, 90 triangles that we can use because we should remember our rules for 30, 60, 90 triangles. All right, and the last one are hexagons. I always say hexagons are special. So there's a regular hexagon. We're still talking about regular polygons. I'm going to draw the little triangle in here. There's our center, our apothem, and our radius. The central angle of a hexagon, 360 divided by 60 is 60. And this is half a central angle. So that's a 30-degree angle. And that makes that angle a 60-degree angle. So we have a 30, 60, 90 triangle inside a hexagon that we can use to find missing pieces. And we also just make a note here, that's half a side. So then we can use these ideas to find missing pieces. We can find a radius if we need it. We can find an apothem if we need it. We can find a side if we need it. Use it with hexagons, squares, and equilateral triangles. All right, so let's look at a couple of examples of using these special right triangles inside of our polygons. So the nice thing about these, let's start with an equilateral triangle, is we only need to know one thing about our shape to find the area. So all we know is this is an equilateral triangle and the side is 14. And we want to find the area. What I like to do for these, for an equilateral triangle, is just divide it in half. We decided that side isn't at the height of the triangle. And this is a 30, 60, 90 triangle. So how long is this side of the 30, 60, 90 triangle? 7. How do we go from is 7 the short, the long, or the hypotenuse for the 30, 60, 90? Short side. How do we go from the short to the long? Multiply by square root of 3. You multiply by 2 to get the 14. So the height equals 7 square root 3. What's the area of a triangle? The formula. Base times height divided by 2. What's the base of the equilateral triangle? The equilateral triangle, the whole big triangle? 14. So the area is 1/2 the base, 14 times the height, 7 square root 3. This would be a question where it would say leave your answer in simple radical form. So half of 14 is 7. 7 times 7 is 49. So I get 49 square root 3 square units. And that would be that area of that equilateral triangle. All we needed to know was the side. Questions on that problem? All right, let's look at a couple of hexagons. Here is our regular hexagon, and this is 10 inches, and we want to find the area. Well, we don't have all the information we need yet to find the area. What piece of information do we need to use in our formula? What has to go into our formula to find our area? The apothem. We can find the perimeter. We need the apothem. What are we going to do to find it? Find the center, draw our triangle. That's our go-to technique. Draw our little triangle. There's our center. There's the apothem. That's what we need to find. Well, that's a 90-degree angle. Drawing my radius. There's the little triangle that we've been talking about. This is our 30-degree angle, and that's our 60-degree angle. If it helps you, redraw this triangle outside of your hexagon. Well, what other piece of information about this triangle do we know? The short side is 5. That's half of a side length of our hexagon. We're going from the short to the long. There's the apothem. What do we do to go from the short to the long? Multiply by the square root of 3. So apothem equals 5 square root 3. The perimeter of this hexagon is going to be what? Hexagon. There we go, 60 inches. So that's in inches, that's in inches. So the area equals 1/2 the apothem, 5 square root 3 times 60. I want to leave my answer in simple radical form. So I'm going to do 5 times 60 and divide that by 2. And I get 150 square root 3 square inches for my area of that hexagon. All right, let's look at one more example. Another hexagon. Regular hexagon. We want to find the area. And for this hexagon, all we know is the apothem. So all we know is the apothem, 4 square root 3. What are we going to do? We're stuck. Give up? We could try. Yeah? Okay, so draw in the triangle to help you visualize it. There's a triangle that we're talking about. That's our 30-degree angle. That's our 60-degree angle. We can figure out that piece. What do we do to go from the long to the short? Divide by square root of 3. So 4 square root of 3 divided by the square root of 3 is just 4. So how long is the side? 8. So that whole thing is 8. So now we're set. The perimeter is going to be 8 times 6, which is 48. The apothem is 4 square root 3. So our area is 1/2 the apothem, 4 square root 3, times the perimeter. Half of 4 is 2. 2 times 48 is 96. So I get 96 square root 3 units squared, or square units, would be the area of that hexagon. So we can use our special triangle rules to figure out other pieces of this little triangle that we draw in our hexagon. And again, if it helps you, redraw this outside the hexagon. Figure out that side. All right, questions? Okay. All right, don't forget that on Monday, I have signed page 626. That's going to be due on block day as well. And we also have Common Core 17 and Algebra Review 21 that's due on block day as well. So all three of those things.